Welcome to all. In this class, we are going to see the semi-classical treatment part 2. That is matter radiation interaction. Particularly, we are going to see the emission and absorption process. Consider the Schrodinger wave equation for a free particle, which is equal to IH cross delta psi over delta t is equal to minus H cross squared over 2m delta squared del squared psi. In presence of electromagnetic field, the Hamiltonian can be written as H is equal to 1 over 2m p minus e by c a whole square. This a we have seen in my previous class, that is semi-classical treatment part 1, that a is the vector potential and plus e pi. Pi is the scalar potential, and we have seen these two are the auxiliary parameter. Since P and A do not commute, the Schrodinger equation in presence of external electromagnetic field thus takes the form, that is we are squaring this A squared, that is P squared over 2m P squared, this one. E minus already there is 2m sorry, plus E squared, because we are taking A squared P squared, so E squared minus 2m C squared, because 2m is already here, this C will become C squared, naturally the A will become A squared, minus it is not 2ab because P and A will not commute, minus AP, that is A is A is equal to P. Of course, this constant will come 1 over 2mc E by 1 over 2mc into P dot A. P is A is P dot A. Similarly, A dot P here. A dot P will come. Of course, this last term E pi, and we have taken into account of the potential V, external potential V. These three terms, 1, 2, 3, 4. These four terms related to electromagnetic field, and this is external potential. Now we will see what will happen to this. As I said, the V is additional potential energy. Uh, V, the potential energy V that binds the particle. Example, considering an electron in an atom. A and pi presents EM potential due to some external electromagnetic force. If EM are very weak compared to V, we can treat them as perturbation. That is, we can treat the electromagnetic field as a perturbation. Here, I like to highlight one important point. We are taking EM field as weak in comparison with this potential energy V. Hence, A squared is very small, and we can ignore this term. The second term we can ignore, and also uh, replace P by its operator. So this P squared will become IH cross del whole squared, which will become minus H cross squared del squared. Similarly, this one you will get IH cross, here one minus, so minus IH cross will become plus IH cross del. So this will be the del. We are replacing P by its operator. Similar is the case here. So it will become minus IH cross will become, because already there is one minus, will become plus IH cross E over uh, 2mc over 2mc plus E pi. This term we are keeping as it is plus V. Here only these two form minus AP minus PA, because A and P will not commute. Then we will see what will happen to this expression. Just now we arrived with this expression. Here one important thing is We have taken pi as 0 for weak electromagnetic field. We have taken pi is equal to 0, so this term will get cancelled. You will get other four terms alone. We will see what will happen to this. Uh, Specifically, you take the second term, that is I h cross E over 2mc divergence A. Remember that there is a psi outside the bracket. Hence, this will become I h cross E over 2mc divergence A pi. So, if you differentiate A first, then psi, you keep psi as it is, you will get A divergence del psi. Uh, Plus, now you differentiate psi and you keep A as it is, so you will get psi divergence A. You know, according to Coulomb Gauge, this divergence A will become zero. Only it retains the first term, that is I h cross E over 2mc A divergence del. There is one more term here, which is exactly same as this one. IH cross E over 2mc A divergence del. So if you add these two, you will get IH cross E over MC A divergence del. You may ask the question why you cannot take psi for here. If you take psi, this is single term only. Here only you are getting del operation for uh, two variable, that is A and psi. So we are not taking out the integral for other terms. So naturally you will get I h cross E over MC because you are adding this and this. So naturally you will get MC. A divergence is A dot del plus V psi, which is equal to I h cross delta psi over delta t. So we end up with this expression, that is we got only three terms. Now you rearrange the term. I am bringing V as a second term. This entire thing, which I have shown in the rectangular red color box as H naught. So in earlier cases we have taken V as a perturbation, but since V is high in comparison with the electromagnetic field, we are taking this as a unperturbed Hamiltonian. We are taking only the electromagnetic field, weak electromagnetic field as perturbed Hamiltonian, that is H prime. That is H prime is equal to I H cross E over MC A divergence del. Which is equal to, of course, I H cross T psi by dt. In free space, you know, J is equal to 0, rho is equal to 0. We can exploit the gauge freedom. We can choose according to our convenience the parameter to make divergence A is equal to 0 and rho is equal to 0. This is known as gauge fixing. With this gauge choice, we can show that electromagnetic field satisfy the wave equation delta squared A minus 1 over C squared. Sorry, this is del squared A minus 1 over C squared delta squared A divided by delta T squared, which is equal to 0. And both E and P are perpendicular to the propagation vector. That we know very well. That is, EM wave is a transverse wave. Now our task is to find the solution for this wave equation, which we know already. We know the solution for wave equation based on A, that is A, which is a function of R and T, is equal to A naught e power I k r minus omega t plus A naught star e power, because this is the complex conjugate of the first one, e power minus I k r minus omega kt. However, we know that perturbed Hamiltonian is defined as H prime is equal to I e h cross over mc a dot del. So here you substitute for a. Then if you take right hand side and left hand side inner product with the kn, so you will get k h prime t get n, which is equal to I h cross over mc is a constant we are taking out, and we are keeping this a dot e power I k exponent term. So this will become k, that exponent term, this one, dot del n. Now what I am going to do is I am separating the time dependent part, that is omega t and kr separately. So this will become e power minus I omega t. Here it will become minus of minus plus. So plus I omega t. So since this gradient is for spatial derivative, I am taking the time derivative outside in both cases, and I am separating this into two parts. So which will be equal to e power minus I omega t, this constant term, and this inner product, which is Dirac notation. We are taking this one. And similarly is the case here. Instead of minus omega t, we will get plus omega t I e h cross over mc k a dot star e power minus I k r dot del n get n. This is the final expression we got. We will see what will happen to this. Now we got k h prime, which is a function of t, that is perturbed Hamiltonian with respect to time, time dependent perturbed Hamiltonian, multiplied with get n is equal to e power minus I omega t I e h cross over mc into k a dot e power I k r dot del get n e power I omega t plus I omega t I e h cross over mc k a dot sorry a zero star e power minus I k r dot del then get n. We know the according to the first order time dependent perturbation, we know the probability amplitude, that is ak, which is a function of time, ak1. One represents the first order time dependent perturbation, which is equal to 1 over I h cross integral between 0 to tau e power I omega k n t into k h prime t uh, into get n, differentiating with respect to t. Now, in the place of k h cross this product matrix, k h cross t n, you replace this one. Just to replace this one. 1 minute is cancelled. Uh, you replace this one, this term. Then, if you replace that, uh, the inside the bracket, I have put this term. That is e power exponent term and some constant term and this product, which is represented by the Dirac notation. Same thing. I have inserted these two terms inside the instead of this one, that is the perturbation k h prime t n. I have replaced for this. Now you can rearrange, you can separate out it into two integral. So first integral e power I omega k n t minus this one minus omega t. So this will become e power minus sorry e power plus I omega kn minus omega t, this one. I have multiplied this and this, I kept this constant as it is and this product as it is. We are differentiating with respect to t. Same is the case for second term. That is here one IH cross. I have brought this IH cross here in this integral 1 over IH cross, and this I omega t minus uh, I omega t. Uh, so I am taking this I omega t plus omega kn here. You have omega kn outside the bracket, omega kn plus this one plus I omega kt, which will become e power I omega kn plus omega t plus this constant term and this product, that is which is represented in the Dirac notation. We are taking integration with respect to t. We end up with this equation. Here what I am going to do is I am going to uh, change the notation. After all, this is a change of notation. You take this green color bond one. I am going to represent this hereafter as k h prime a n. This a represents the absorption. Within a short period, you are going to understand why it is called absorption perturbation. Similarly, here you see the red color bond, which we are going, which I am going to label it as k h prime e get n. This E represents emission process. So we will this also we will understand in a short period. See, here you should remember that we have taken time dependent component outside. That is e power plus or minus omega t only the time dependent component that we have taken out. So this one will be the time independent component. So I am going to take out this green color product and then this red color outside the integral. So I am going to differentiate only the exponent term, which explicitly depends on the time. Finally, we end up with this expression. Now our task is to carry out the integral. So if you integrate the first term, you will get e power I omega kn minus omega t divided by I omega kn minus omega. If you substitute the limit 0 and tau, the upper limit is tau. So the first term in the numerator will become tau. T is replaced by tau because it's the upper limit, and the lower limit is 0. So e power 0 is 1. So that's what I have written. Of course, in the denominator, I omega kn minus omega will come. This is for the first term. Similarly, for the second term, you can see here, instead of minus, here you will get plus. So and also there is a I here. If you multiply this I with this I, you will get to I squared, which is minus 1. I have taken this as a minus 1 over h cross. Same thing I did for second one, that is this I, and multiplied with this I, you will get I squared, which is minus 1. So I got this expression. We arrived with this expression. Uh, if you see this expression carefully, you can understand one important thing. That is, here any one of the term will be the dominant. Say, for example, if omega kn is equal to omega, then this term will be, first term will be dominant, because this will become, the denominator will become 0, so this will dominate. Uh, Otherwise, if omega kn is equal to minus omega, then naturally this term will get dominate, because omega kn minus omega will, denominator will become 0, so this will become dominant. So we can ignore the first term. So depends upon the condition, either we can ignore the first term or second term. Now let us consider the first term to be dominant. That is H cross k omega is equal to H cross omega, this one. So which is equal to H cross omega kn is equal to nothing but the difference between the final energy and the initial energy, Ek minus En, which is equal to H cross omega. Then Ek is equal to, if En goes to right hand side, this will become plus En. So Ek is equal to En plus H cross omega. So that means the final energy is higher than the initial energy by an amount H cross omega. That is, it observed one photon. So this is called, the first term is called absorption process. Similarly, for the second one, for second one, H cross Kn is equal to minus H cross omega, because here H cross is after all constant. That means omega Kn is equal to omega. Now, you know very well, this is the energy difference between initial state and final state. So Ek minus En is equal to minus H cross omega, which is equal to Ek is equal to En minus H cross omega. So here initial energy is reduces by the amount H cross omega. That is, it emits one photon. So if this E is justified. So the first term is absorption process, and second one is emission process. We have end up with this expression, and you should remember that you have to keep in mind that this green color uh, term, that is bra k h prime a get n, is equal to I e h cross over mc k a naught e power I k r dot uh, del get n. So this is this what we have earlier defined as k h prime a n. So that we have to keep in our mind. Similarly, k h prime e n is defined as I e h cross mc k a naught star e power I k r dot del n, that is get n. This what we have defined earlier. From this, we can understand that the probability of finding the system in the final state k is proportional to this modulus square of this one, this left hand side, or the modulus square of this one. Or you can see in both the cases you have n, sorry, a naught, a naught, a naught star. So it is proportional to modulus of a naught square. That means it's a naught square modulus of a, if it is proportional to modulus of a naught square, then it is a intensity. uh, because the square of the amplitude gives you the intensity. If the intensity of EM wave is is in small frequency range delta omega, then it can be represented as I omega. That is frequency depends on the intensity depends on the omega into delta omega. Then we can write take that is take the average of the pointing energy over the period of oscillation. This is well established one, that is modulus of a naught squared is equal to 2 pi c divided by omega squared I omega del omega. So many times we have seen this as a final expression for probability amplitude. Now let us take that this first term, that is absorption term, dominate. Then you can ignore the second one. Then the probability is that is probability is equal to the modulus square of the probability amplitude. This one is probability amplitude or expansion coefficient. If you take modulus square of this, you will get the probability. This is the probability of the particle to move from nth state to kth state. So which is equal to 1 over h cross squared. Just you take the modular square of first one. So naturally you can ignore the negative sign. This will become 1 over h cross squared, and modulus of this k h prime a n whole square, and this one square. This exponent term including denominator whole square. If you take the square of the numerator, we have done it already in our lecture, that harmonic perturbation. That is e power I theta minus 1 whole square is equal to 4 sine squared theta by 2 divided by theta. If you apply that rule, you will get here in the place of this exponent term, you will get 4 sine squared omega kn minus omega tau divided by 2, um, divided by this denominator omega kn minus omega whole square. This is the expression, probability term we got it final. And you remember that by definition we got this k h prime a n is equal to I e h cross over mc, and this one k a naught e power I k r dot del n. Similarly, a naught squared, we know a naught modulus of a naught squared is 2 pi c over omega squared I omega delta omega. Then what you will get about this probability, that is ak1 modulus square. So already you have 1 over h cross square. Now you replace this by this one. That is here you have a into a squared. You take the a squared term, which I have shown in the red color bond. So this will be 2 pi c over omega squared I omega delta omega. This is for a dot modulus squared. And about this, you have to square this also. You have to take modulus of square of this term. We will see what will happen to that. Then because a we have taken out, because a is constant, we have taken out. Inside this product, you will get k e power I k r dot del n whole modulus squared, and this sine squared term. So now we end up with this expression. Now you take modulus square of this green color part. You will get, of course, I squared is minus 1. Modulus means it will become plus, so you can ignore that. You will get 2 pi c e squared h cross squared. E squared h cross squared. In the denominator, you will get m squared c squared. And now what I'm going to do is, you can carefully analyze this equation. This h cross squared, I have marked with the yellow highlight. H cross squared will cancel out this h cross squared, and this c will cancel out with this c squared. You will get only c in the numerator. Here there is one 2, here there is one 4. 4 into 2 will become 8. So now after reducing the term, you will get 8 5. That is 2 plus 4 8. This 5 e squared, because h cross squared will get cancelled. In the denominator, you will get omega squared m squared c, because this c squared will get cancelled with this c. Remaining thing I have written as it is, except this 4 I have brought here. Finally, we got this expression. Now consider the absorption process. The probability of the transition for Ek is equal to En plus h cross omega at the time t is uh, thus considering the EM radiation is not monochromatic. Remember that is important point. EM radiation is not monochromatic. That means it has range of frequency. That range only we have taken as delta omega. Since it has a range of frequency, Here, what we are going to do is we are going to sum over all the frequencies. That is summation over omega. This entire term will come. And what about this integral? After all, we have rewritten this Dirac notation into integral form, which is equal to UK star. UK star is Pra K, nothing but Pra K. And already you have e power ikr dot delta del so this is del a I have used to subscribe. It indicates the propagation is along the direction of a, that is the vector potential, and get n will become un. This green color font is nothing but I have changed the Dirac notation into integral form. That's what I have done it here, nothing else. And the sign term will become as it is. Finally, we got this expression for square of the probability amplitude. As I mentioned, del A is the gradient operator along the polarization vector A naught. And here I like to highlight a few important points. Let us say there is no phase relation among different frequency of contribution. The frequency interval delta omega can be made infinitesimally small, and the summation over omega can be replaced by the integration. The summation, when it is going to small, you can replace the summation over integration. However, when omega is equal to omega kn, we will get maximum intensity, and this delta omega is tends to zero, very narrow, very small. Then this will become, this omega squared will become omega kn squared, and similarly the I omega kn. Omega kn, and we are taking the integral of the sine term because its frequency is very narrow, so we are taking the integral for this sine squared term also. And of course already this is the integral part. Moreover, here we are dividing it by time tau. So I am dividing with the tau both left hand side and right hand side. So finally, we got this expression. Now we will see some of the interesting phenomena. If you integrate this sign factor between minus infinite to plus infinite, you will get pi by 2. So if you multiply this equation by pi by 2, because we are the result of this one is pi by 2, so this pi will become pi squared. 2 will cancel with this 8, so this 8 will become 4, and of course this integral, you will get this integral where the magnitude of k is equal to omega kn pi c. This is also you know very well. So this is for the upward transition. Similarly, for downward transition, in order to differentiate this downward transition, I am replacing k by k prime. That's all. It's a matter of notation. So ek prime is equal to en minus h cross omega. So this will become like this: 1 over tau ak prime 1 modulus squared is equal to this one. Exactly the same thing we will get, except this k will become k prime, where the magnitude k is now omega k prime n divided by c. Thank you very much for watching my videos and supporting me. If you have any questions and if you need any clarification, you can contact me through my mail ID vasumku@gmail.com. I will try to answer it at the earliest through mail or YouTube videos. My YouTube channel ID is www.youtube.com/c/vasuvphysics. Thank you very much.